Hello and welcome back to Manifolds, the video series where we talk about analysis and integration on generalized surfaces. And indeed, in today's part 51, we continue our discussion about the exterior derivative on manifolds. You know, this one is also often called Cartan derivative and denoted by a lowercase d. And today we will show that this d operation is compatible with smooth maps between manifolds. And one usually calls this the naturality property of the exterior derivative. However, as always, before we start with the details, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, you can use the link in the description to download additional material for the videos. And then without further ado, let's immediately start considering a manifold. So let's say here we have an n-dimensional smooth manifold M. And now you already know we can consider k-forms, differential forms on this manifold. And the set of all these k-forms is denoted by omega k. And now our Cartan derivative goes from omega k to omega k plus 1. And the common notation for this exterior derivative is dk. However, you might remember that often we just omit this superscript altogether. So by definition here, if we start with the k form omega, then the Cartan derivative gives us a k plus 1 form on M as well. And in the last videos we have already discussed some important properties of this exterior derivative for k forms. For example, for zero forms, this d operation is our standard differential for smooth maps. And moreover, in a special case for 1 forms on R3, we also have seen that this exterior derivative is the curl of a vector field. However, this important connection we will discuss later in more details, because today we will look what happens when we use smooth maps. So let's take a second manifold n and a smooth map from n into M. Indeed, the dimension of the new manifold n can be different, because the only thing we need now is a smooth map between manifolds. And then we already know that any k-form omega on M can be pulled back to n. And as you might recall, the notation for this pullback is f star omega. So by definition, this is now a differential form on the manifold n. And for the sake of completeness, let's quickly recall how this one is defined. So first, our differential form gets a point P as an input, and then just k vectors from the tangent space. And then the value that comes out is just defined by using our omega on M. So more precisely, omega at the point f of P, and then the tangent vectors get pushed to M by using the differential of f. So this is the whole definition, the pullback of a differential form. And now the nice thing is that our exterior derivative here is compatible with such a pullback. Which simply means it does not matter if we use this d operation before the pullback or afterwards. So you could say that we have some commutativity between these two operations, and that is what we call naturality in the end. So let's put everything into a proposition which we can formally prove. But first we need the statement, and the assumption is that we have two smooth manifolds. And in addition we have a smooth map f from n into M. And then what we take is a k-form omega on the right hand side. And then as before, we can look at the pullback f star omega, which is a k-form on n now. And for that we can use our exterior derivative, which means we make a k plus 1 form out of that. And as already mentioned, we could also do that on the right hand side by using omega. And now obviously we could also form the pullback of this k plus 1 form. And now the nice result is that this is actually the same as using our Cartan derivative after the pullback. So you can just remember that you can push the d operation through the pullback. And often in mathematics we just say that this Cartan derivative is a natural transformation. Okay, so this is the next property of our exterior derivative which we want to prove. And since it has to work for all k forms, it's actually a proof by induction. And the simplest case would be k is equal to 0, where omega is just a zero form, so a smooth map. Therefore, instead of omega p, we can just write g of p. Then we simply don't forget that we cannot put any tangent vectors into this k form. So again, g here is just a map from M into R. Which also means that the pullback for f here gives us a map on N. So please don't forget the picture, our smooth map f goes from N into M. And there you might already see that in this case the pullback is just a composition of maps. And this is not hard to see because we can just use the definition from above again. So we don't put any tangent vectors in, so we just have omega at the point f of p. And of course omega at the point f of p is just g at f of p. And by definition, this is the composition of two maps. So if we want, we can write g after f. And this is quite nice, because it means if we use our exterior derivative, we just have to apply the chain rule. So let's immediately do that. Let's write it down for a chosen point p. And then the standard chain rule tells us that we have dg at the point fp times df at the point p. So nothing special, this is just our standard chain rule. However, please don't forget, after applying this d operation, our exterior derivative, what we get here is a one form. So there we can finally put in a tangent vector v1. And if we do that on the right hand side here, you might recognize the definition of our pullback. Simply because dg is also equal to d omega by definition. So we have d omega at the point f of p, and we put in the tangent vector transported by the differential of f. And now if you recall the definition from above, this is just the pullback of d omega. Of course at the point p and evaluated at the tangent vector v1. And that's it. This shows the equality for zero forms. And now I would say, in order to make the whole proof easier to digest, we can also look at the next special case. So now what happens if we look at one forms? And to answer that, as always, we just look at the whole thing locally in one chart. So this chart is the set U together with a map H. And we map everything into Rn, and the inverse of H is denoted by phi. And then under this assumption, our omega can be written as a finite sum of standard one forms on this chart. And these are denoted by dx1, dx2 and so on, and we also have component functions in the front. And please don't forget, we write dx, but these are actually just components of dh. So you see, for one form omega this is quite simple, we just have to combine these standard one forms dx1, dx2 and so on. And now in the next step, we can just apply our pullback f star to the whole sum. And there we can already use a property we already know for the pullback f star. Namely, it's nicely compatible with the wedge product of differential forms. Which simply means we can apply the wedge product before or after the pullback. And there it does not matter from which order we have our differential forms, because it always works in such a product. So now we can do two things. First, we can push the pullback into the sum, and then we can distribute it over the two factors of this product. So please don't forget that here we actually also have a wedge product between a zero form and a one form. So also here, the formula from the right hand side is applicable. So this makes everything quite simple, because we just have new component functions and new one forms. Therefore, it should be no problem at all to apply our Cartan derivative now. So we just apply d to this one form, so what we get out is a two form now. So first we can use the linearity, and then we have to apply it to a product. Which simply means that the product rule for our exterior derivative comes in. This one is not so complicated, because it looks really similar to the standard product rule. So first we apply d to the first vector, and then we have the wedge product with the second vector. Afterwards, in this case we have plus, and then the opposite order. And there we don't have to write a wedge product, because we have the zero form in the front. Okay, so this is just the result of the product rule, and now we can look at this second term. There we can already apply our case k is equal to 0 from above. And then we see we can just pull out this d operation. So we have d f star of the mu1th component of h. This is the real valued function where we apply f star to. However, then we see that we have this exterior derivative 2 times in a row, which by the complex property immediately tells us that the whole term is equal to 0. And this is a really nice result because it tells us only this first term remains. And also there we can use our first case to exchange the d operation with f star. So you see what remains is this one form here wedged that one form. And then of course we can also write this pullback f star in front of everything. And this is quite nice because there we recognize that we have d omega in the middle. Indeed, this is what we get when we apply d to omega itself. And there we have it. This is what we wanted to show. F star and d commute for one forms as well. And in fact, with this proof here, you might already see how the general argument for the induction works as well. There we would assume that we already know the formula for k forms, and we would show it for k plus 1 forms. So let's say we have eta as a k plus 1 form, which we can also represent locally. And this means we need indices going from mu1 to mu k plus 1. And now obviously what we could do is to split up this k plus 1 form and just consider the k factors at the end. And obviously this is what we can use in our induction argument. So essentially we do the same as before. We first distribute f star and then we apply d with the product rule. So we push everything into the sum and then we can say we have f star of this one form and then wedge f star of this k form. So this is all for f star, and now we can apply our exterior derivative. And as already mentioned, this is not so complicated because it's just the product rule again. So this is the first term, and then we have plus or minus the other order. Actually here we have minus because the first factor is a 1 form. And then please note, in the second term we have df star for this k form. And exactly there, our induction hypothesis can come in. There we can exchange d and f star, so we get out 0 for this factor again. This is the same reasoning as before, we always have 2 times d in a row. And moreover, in the first term we can also exchange d and f star, because we just have a 1 form there. Therefore, as already expected, we can just write f star in the front of everything. And then inside the sum what we get is actually just the derivative of the component functions. However, then of course in the wedge product with dx mu1 and the wedge product with all the other terms at the end. And then you might recall that this is actually just the definition of d eta. So exactly what we wanted to show, and now the induction is finished. And this finishes the proof of the naturality of the Cartan derivative. And indeed, this fact is quite helpful because we will often shift around with a smooth map f. And how we can apply that, we will definitely see soon. So let's definitely meet in the next videos again and have a nice day. Bye bye.